Part A, heap sort. I plan to use 2 classes this week, because this part relatively long to complete this part. All right. 8.1, Introduction to Heap Sort. Let me get my remote control ready. All right. First, let's look at the motivation part. Why we need to study another sort. All right. For our sorting problem, this time we need to consider some special requirements. So in our real world applications, so many times you may not just apply the general sorting algorithms. So many times when you apply a specific sort, you need to consider some special business requirements. Here, let me give you a few requirements. All right. The first one, we need to control the worst case efficiency. So we want to avoid the bottleneck, right? Remember, for the worst case bottleneck, so here, I just remind you, remind you that big theta, that big theta of n squared, right? So this very slow bottleneck, due to some reason, for some special business consideration, people may like to avoid this kind of worst case bottleneck. All right, so that's the first requirement. Currently, we have learned 5 sorts, right? So among those 5 sorts, which one do you feel it can satisfy this condition, this requirement, among the 5 sorts we have learned so far? Can you think of some specific one? 5. Merge sort. Merge sort. Only merge sort satisfies this requirement. The other 4, no. That's for second. We have other requirement we need to. The second one is, all right, in place. Right? In place. Remember? So here, let me recall a little bit. This in place means the in place algorithm, okay? Not in place elements. Some students got confused. In place elements, so that's the usual understanding we have. But we have another concept. In place algorithm, that means the extra space. Lauren? Question? Okay, So let me remind you the special meaning of this in place algorithm. So here I want to, give the algorithm. Okay, that is the extra space. I mean, the writing not normal. Let me. I need to charge this pen. Charge the battery. So this one. This pen, something not quite right. So the extra space in big theta of 1, right? Yeah. So that's the meaning of the in-place algorithm. That's the second requirement. Yeah. So this requirement, yeah. Let me just recall a little bit what we discussed last time. All right. When you use the extra space, you need to consider the whole process of sorting, whole process. You cannot just only look at some one or two steps. Yeah. So what's that? Because if you look at some special steps, in those steps, you can get in place. You use constant extra space. But, yeah, remember last time I mentioned recursion. When you need to do the recursion, we need to use a stack, right? Deep stack. When you need to use deep stack, you cannot control the extra space used, right? Yeah. So that kind of problem you also need to avoid. That means you try to avoid the recursion. So in this algorithm, you need to, other than the in-place consideration, another important consideration is you need to avoid recursion. Otherwise, the stack part, we cannot treat it as in place due to the stack part. Yeah. So this is requirement number 2. Requirement number 3, another important situation in our business, real world business applications, maintain dynamic data efficiently. Yeah. So here, yeah. So this special requirement we need to spend some time to understand. So what's the dynamic data? Yeah. Actually, it's very common in our real world application. So the data comes in dynamically. Yeah. So when we apply our sorting algorithms, yeah, the data keeps coming in. Yeah. So we need to insert the data in our storage collection. Okay? Yeah. But when you add new data items, you need to consider the efficiency. How efficient when you add new data. Yeah. So that consideration. Yeah. Think about if we use an array to store the data, when you add a new data item, first, you need to consider, can you preserve the order information? If you want to do insertion, if you need to do the shifting operations, yeah, because when you need to insert the new element into its right position, you need to do a lot of shifting operations. When you do that, too costly, right? Yeah. Too costly. Yeah. Yeah. So here, this step number 3, very important. All right. So in order to design a new sort that satisfies all these 3 requirements, that's not easy. That is not easy. That means none of our current current the sorts we have learned at this point can satisfy these 3 requirements. None of the 5 can satisfy these 3 requirements. So that's the reason we need to design a new one. Yeah. But for this one, in order to make the new sort satisfy these 3 requirements, You need to do a lot of work. Okay, yeah. So when you look at the title of our Module 5, Advanced Data Structure, so we need to build some advanced data structure for the sort. Yeah. So that's the special work we need to do for this one. Question?
What is the N squared?
N squared. Yeah, N squared. You remember there are many sorts. Yeah. Remember number of comparisons. Remember 1/2 times n minus 1, right? Yeah, is this, so we use big theta of n squared. Yeah, because the growth function, right? Yeah, the growth function n squared. So we use growth function as the representative for the whole class of these algorithms. Yeah. Yeah. So that's very slow. Yeah. So when we see n squared, for this step, we know it's very slow. Okay? Yeah. So we want to avoid it, the problem. All right, let's continue. Yeah. Continue, but I need to explain further this dynamic data consideration. All right. Yeah. So for this dynamic data, efficiently, yeah. All right. So now we need to work on the data structure design. Yeah. So this advanced algorithm relies on some advanced data structure. Yeah. Yeah. All right. So here, yeah. So when we talk about so in our data structure design, the question, what do you mean efficiently, right? Yeah. So I need to explain how fast you can treat it as efficient, right? Yeah, because it's a subjective term, right? Yeah. So here, actually, we have some objective description. Yeah. When you do insertion, if you have big theta of n, that's the linear insertion, right? Yeah. This big theta of n corresponds to the linear insertion. Yeah. So linear, we know, yeah, 1 by 1, yeah, that's quite slow. Yeah, based on our impression, that's quite slow. Okay? Yeah, linear, all right. Yeah. So we don't want to have the efficiency as slow as linear increase, but we want the big theta of log n, that's the binary insertion. How about that? Log base 2 of n, that's the binary insertion. That's very fast. Okay? Yeah. So it corresponds to the efficiency like the binary search. Yeah, we know binary search. People feel, yeah, very satisfied. Yeah, so fast, binary search. So here we want to make our data insertion as fast as the binary search. Yeah, so that everybody should accept this efficiency. Okay, yeah. So our goal, let's target the binary efficiency. Okay, all right. Now, then, so let's look at the implementation details. Yeah. So for the data structure design here, yeah, because in order to get the binary efficiency, should we use some binary tree structure to store our data? Yeah. You have to have some suitable storage special data structure, right? Yeah. So that storage structure should have the binary tree properties. Yeah. Binary tree properties. Yeah. All right. So that's the starting point. Then let's keep investigating the binary tree structure. Yeah. And we want to make it as simple as possible. Yeah. So next step, we want to consider what specific way we want to use to store a binary tree to organize our data. Yeah. All right? And we want some special, we want some simple storage structure. Well, so not complicated, so we need to do a lot of work. No. So we want to as simple as possible. Yeah. All right. So then the candidates. Yeah. So let's look at our basic data structures that we can use to store a binary tree. All right, yeah, candidates. The first one, array, right? Yeah, so array always the simplest data structure. So we should include array. Yeah. How to use array, that's another question, right? At least we put it as a candidate at this point. Yeah, just candidate. Yeah. But another one, linked list. Another data structure, basic data structure, linked list, because there are links inside this data structure. We can use certain links to point to other nodes, right? Yeah, it looks like fitting the binary tree requirement naturally, right? Yeah, linked list. Yeah. We include as another candidate. Yeah. All right. So let's just consider these two. Yeah. For the array, yeah, simpler, right? Yeah. Yeah, because array much simpler than linked list, right? Yeah. Linked list much more complicated than array. Yeah. All right. Yeah. So the question is, if we want to use an array to store a binary tree, how can we do it? Right? Yeah. Because in a binary tree, we need to specify child nodes, right? Left child node, right child node, that relationship, right? Yeah. But in an array, there is no natural way to specify it, right? Yeah. Not given, at least, not given naturally. All right. You need to do more work. Yeah. All right. Yeah. So that's the, technical difficulty. All right. Yeah. So next, yeah, maintain dynamic data. Yeah. All right. So So now we want, based on our understanding, to maintain dynamic data efficiently. So we need to, So here the question is this: if you use array directly, you cannot maintain dynamic data efficiently. So here the question is, if you use array directly, you cannot, because array has the sequential structure. When you do insertion, then you need to do shifting operation, linear shifting. So then you cannot do efficiently. Because you use the natural given structure of an array, that's not enough. That's not enough. You have to add new structure properties into that array in order to get a, faster insertion, binary type insertion. Okay? You need to add a new structure. So if you want to use array, you have to modify it. Okay? Yeah. You have to do more design work. Yeah. Data structure design work. All right. Yeah. Because the linked list, because it's too complicated, we want to avoid it. If we can make array work, then we don't want to use linked list, right? Yeah. Yeah. Too complicated. Yeah. Yeah. All right. So next, we try to make array work. Yeah. We try to make array work. then, yeah, so we'll be very happy. Yeah. All right. Yeah. So now to do that, build a binary tree in an array. That's our goal, current goal. Yeah. We need to build a binary tree. How to store a binary tree inside an array. So that's something we want to do. Okay? Yeah. So not trivial, right? Yeah. Yeah. So here you need some smart idea here. Okay. Yeah. So how to modify the array? Yeah. All right. So data stored in the array. Yeah. So here. Yeah. So let's see. Yeah. So here we need to assume. Yeah. So the array is sorted. Yeah. Because when we process given data dynamically, yeah, so we have chance to gradually organize our data, right? Yeah. So we can gradually get our data organized. Okay? Yeah. So assume sorted. Yeah. But when new data comes in, you need to insert a new data item into an ordered array. So then think about how much work we need to do, right? Yeah, because there is a existing order. You need to do some work to include the new data item without breaking the order. Yeah, all right. In that consideration, yeah. So then, yeah, here. When you do the insertion, yeah, so the linear insertion is not acceptable. Yeah. So this is the linear insertion. Okay, yeah, we know corresponds to linear insertion, too slow, so it's not acceptable, right? Yeah. So our target is binary insertion. Yeah. So this corresponds to the binary insertion. Yeah. So this is the, desired property we want to have. Okay, all right, yeah. So for the insertion, yeah, so linear search and a binary search. Okay, yeah. So because, when we do insertion, we need to find its location. Then we need to do data manipulation. Okay, after we find the location, we also need to do data manipulation. Yeah, all right. Yeah. So for the binary type insertion, if we have a binary tree, first we can find the location in the tree quickly, right? In a binary tree from level to level, to traverse operation level by level. Yeah, so that's very fast. Yeah. Because we do not need to go through all the nodes, right, in the binary tree. We only need to, traverse the nodes along certain paths. Yeah. Here I need you have some basic binary tree background. Okay. Yeah. So here let me just draw some simple binary tree. Yeah. So what I'm talking about, yeah, all right, yeah. So if we organize our data in this binary tree, then when you need to find the location, you need to traverse this binary tree, right? Yeah, along some path. Yeah, yeah. All right. So so how many comparisons do you need when you traverse this binary tree? You need to look at the number of levels of this binary tree. Number of levels. If this binary tree is quite balanced, then you can control the number of levels of the binary tree. So here, in our design, we need to think about our binary tree should be quite balanced. It should not be unbalanced. If it is very unbalanced, then your traversing path could be very long. If it's long, then you need too many comparisons. Now, in order to control the number of comparisons, you want to make your binary tree as close to balanced binary tree as possible. As close to binary tree as possible. Okay? All right. So that's another important consideration to control the efficiency. All right. All right. How to get it? Yeah. So after you understand what do you need to achieve, next step, we want to make it happen. So next step, we can, make our data structure, new data structure, to be able to have all these properties. All right. Yeah. Need to introduce this new data structure with arrays as its underlying data holder. Yeah. We use the locations inside an array to hold all the data items underlying. Yeah. But we need to organize our data a little bit in an array. Yeah. We need to do some extra work to make our data organized in this array. Yeah. All right. So next. Yeah. The key step we need to make it happen is we need to define an appropriate parent-child relationship. Binary tree, you need to specify parent-child relationship. So in an array, how do you define valid parent-child relationship among nodes, right? That's challenging. That's the current challenging design work we need to do. Okay? Yeah. Parent-child relationship in all the elements inside an array. Yeah. All right. To do that, now our 8.2 binary tree structure in array. So we need to focus on that parent-child relationship. All right. All right. Yeah. So when we do this, all right, yeah, when we build a binary tree inside an array, yeah, our main technical problem we need to solve is this parent-child relationship. It must be simple. First, it must be simple. Second, it must work well. Yeah. So we can do all the operations we need. Yeah. All right. Yeah. Now, the heap data structure. This time we introduce this heap data structure. What's that heap data structure? Okay. All right. Yeah. Heap. Yeah. So inside memory, yeah, so this heap concept is used, quite a lot in main memory management. Yeah, so heap used quite a lot. Yeah, but for our, software-oriented students, yeah, so we do not need to look at a lot of details inside main memory, right? So mainly we work on the algorithm part. Yeah. But this time, we need to use a special data structure called the heap. First, let me describe this heap data structure. So what is a heap? Yeah. The properties we need for this new data structure is, first, we use an array as underlying storage object. Yeah. So that's we know. Yeah. Next, near complete binary tree, right? As I described it, when you do, traversing of your binary tree, you want to control the number of comparisons. Yeah. So for that reason, we need near complete. Yeah. So what's near complete? Yeah. So I need to explain. Yeah. So, all right. First, complete binary tree. You all know, right? What is a complete binary tree? Yeah. So let me start with this complete binary tree. Yeah. All the levels are full. Okay. That's complete. Yeah. So let me draw a simple complete binary tree. Okay. Yeah. Binary tree. All right. All the levels must be full. Let me draw another level. Okay. Yeah. Yeah. So this bottom level, yeah, yeah, also must be full. Okay. Yeah. So although here I skip some nodes, yeah, because I do not have a lot of space. I skip some nodes. All right. But the property you can see all the levels must be full. Okay. Yeah. All right. That's complete binary tree. For the complete binary tree, the number of nodes n must be power of 2 minus 1, 2 to the k minus 1. If the n has this structure, power of 2 minus 1, then you can organize all your elements in the array in this complete binary tree format. Yeah. But if n is not power of 2 minus 1, then you cannot get a complete binary tree. Yeah. All right? Yeah. But for the general m, we do not have this 2 to the k minus 1 structure. No. So for the general n, the next best thing we can do is near complete. Near. Okay? Yeah. But the question, how to specify this near term here? Yeah. Yeah, that's simple. Okay? So all the levels must be full except the bottom level. Okay? Bottom level, we just arrange the nodes in a natural order, whatever it is, we just accept it. So the bottom level may not be full. Okay? But other than the bottom level, all the other levels must be full. Okay? Yeah. That's the near complete binary tree. Yeah. Okay? Yeah. So now we are satisfied. Not too bad. Okay? Because we can control the number of comparisons, right? Yeah. So, only bottom level. Okay? Yeah. So it's another, you won't get a very unbalanced tree structure, right? Yeah, unbalanced. Yeah. So what is a very unbalanced tree structure? Yeah, here. If the tree growing, just along, one specific direction, that's unbalanced. Okay? Yeah. Skewed, right? Yeah. Skewed toward one side. Yeah. Unbalanced. Yeah. Because large part this side you do not use. No. In that situation, when you do traversing in this binary tree, your path could be very long. And number of comparisons you need could be big theta of n. Big theta of n. Yeah. Yeah. So we don't want to have that structure. Yeah. So all right. So that's the near complete binary tree requirement. All right. Yeah. So as an example, this is a near complete. All right. Yeah. All the levels are full except the bottom level. The bottom level, yeah. Any so number of nodes you used, yeah, just whatever you have at the bottom level, you just accept it. Yeah. So that's the near complete binary tree. All right? Yeah. All right. So now, with the tree structure, now we have the, basic tree structure there. Yeah. So next thing we need to consider. Yeah. All right. Yeah. Sufficient space for dynamic data. Yeah. So here, sufficient. Yeah. So third is this question. Sufficient space, usage. When we look at the space usage, we want to find a we want to allocate, because for dynamic data, think about when you store data dynamically, you need to do space allocation, right? You need to do, memory space, you need to do space allocation, right? Space allocation, okay? All right. When you do space allocation, how much space is sufficient? Think about that. Yeah? Because dynamic data, how much data do you have? You do not know, right? Yeah. Yeah. It's hard to predict in the future, because when you apply your application in a certain period, how much data items do you need to store? It's hard to make a good prediction, right? How to make good prediction, okay? 1,000, 2 million, How can you make a good prediction? It's hard to make good prediction. So there is another technical problem we need to consider. So this is property number 3. So there is a big technical problem. How do we manage our space usage? Now, the question is, how to manage our space usage, right? Yeah. Okay. Yeah. So I will explain this problem more. Yeah. All right. Certain relationship among nodes, parent-child relationship, right? Yeah. So number 4, we need to address the critical parent-child relationship. Number 4. All right. Yeah. So we need to, go through all these things. Yeah. So far, you can see the first, the second, we have done, right? First, second. Yeah. So we don't have any question to answer. Number 1, number 2, okay? We feel comfortable. All right. But number 3, we haven't found a good solution, right? Yeah. Number 4, so we need to find a solution. All right? So number 3, number 4, we need to find good solutions. All right. Question, how much space is sufficient? Now, let's answer, question number 3. All right. So here, remember, when you work on dynamic data, nobody can do a good prediction on dynamic data regarding the sufficient space question. Now, think about it. When you use the array, you need to specify the size of the array, right? At the beginning, what is the size of your array? When you start, you need to pick certain size, right? Yeah. Then your data keeps growing. Then eventually, your array is full. Yeah, because sooner or later, your array is full. Then we know array always has fixed size, right? Yeah. Based on array property, the size of array always fixed. So after you declare the array, you cannot change its size. That's the property of array. Okay. But after array is full, and you have new data items come in, what you should do in this situation, right? Yeah. Think about that. Yeah. So this is a technical question we need to answer. Yeah. You have to answer this technical question. Okay. All right. Yeah. All right. Now, yeah. So here, I like to explain the idea. All right. Yeah. So at least we have some, feasible idea, right? Yeah. How to make array space sufficient for dynamic data. So let me use a diagram to explain this idea. Okay. It is unknown about the amount of incoming data. Yeah. So at the beginning, when you start, you can only allocate appropriate size for your array. Okay? Yeah, at the beginning. Yeah. So assign certain amount of space to the array initially, yeah, because you need in your mind, you need to get ready to enlarge your array, right? Yeah, because sooner or later, you need to make your data storage array larger, right? Larger, yeah. So you need to prepare for that. Keep adding data and monitoring the size closely. Yeah. Every time when you do insertion, yeah, you keep growing. So you need to, keep checking if the capacity of the array is full or not, right? Yeah. All right. So when a threshold is reached, yeah, because when you do the monitoring, checking work, yeah. So you may want to set a threshold, right? Yeah. Threshold. Yeah. Warning. Yeah. This threshold is just some warning sign. Okay. Yeah. You have a certain amount of space in the capacity. Not full yet, okay, certain. But you need to start doing preparation for transition of your data, right? Yeah, because your array will be full quickly. You need to do preparation for the transition, data transition, all right? Yeah, so we will talk about transition question, all right? So a new array, so how to do the transition? Threshold reached, a new array with larger size is created. Yeah, because you cannot grow the size of the old array. Old array, the size is fixed. But how do you store more data? The only way is you create a new array with larger size. Then you copy the data from the old array to new, larger array. Yeah? In that way, you have more space. Yeah? You need to copy the data. So there is a data copy. And copy the data to the new array. That's the typical way people use when the data grows, out of the original capacity. Yeah. All right. So this step 3 is the main step. We need to find a, graceful way to handle this number 3 step, technical step. All right. Usually, it is expensive to copy a large array. Think about, suppose you have an array with 1 million elements. That could happen. No, that could happen. The array, 1 million elements. Now you need to copy data from old array to new array. You need to copy 1 million elements. Think about how fast. How much time do you need? Okay? Yeah. Yeah. Right? Think about it. Yeah. So here I just give you an example. Okay? Yeah. So copy a large array. Yeah. So here let's assume 1 million. Yeah, because 1 million, it's not too large, right? Yeah, relatively large, we can say. 1 million elements. Okay, data copy. But think about how much time do you need to copy 1 million? It's hard to say, but at least 2 or 3 seconds, it's a reasonable estimate, right? Think about it. Yeah. We know our current computer is very fast, right, for data copy. But think about when you copy 1 million elements from one array to another, using 2 or 3 seconds, that's quite reasonable, right? That's quite reasonable. But think about when you do the data copy, all the other work, because when you do the data transition, so this copy, when you do data transition, your business has to stop, right? Yeah, because the data is not ready. How can you do the regular business? Okay, data is in transition. Okay, yeah. So you don't want to touch the data. When you do the data transition, you don't want to touch the data, right? Yeah. Yeah. Okay. You don't want to, mess data, right? Yeah. So in this situation, that means your customer need to wait at least 2 or 3 seconds while you do the data copy. Right? Think about that experience. It won't be very good for your customers. Your customers sit there waiting 2 or 3 seconds. Your application freezes in about 2 or 3 seconds. That's horrible, right? Although 2 or 3 seconds, not long, but it freezes for 2 or 3 seconds. That's still a big problem, right? Yeah. If 2 or 3 milliseconds, then nobody care, right? 2 or 3 milliseconds, then it's acceptable. Yeah, because nobody can notice 2 or 3 milliseconds difference, right? But 2 or 3 seconds, everybody, sit there quite some time. Yeah. Not tolerable. This kind of slow bottleneck performance, not tolerable. Okay? Yeah. So now you have to solve this bottleneck. Delay problem. Data copy, this is a bottleneck. Okay? Waiting time. Yeah. You have to solve this problem. Okay? Yeah. So here the idea is this. All right. Yeah. So I use this peak. Yeah. This curve represent, CPU time usage for the data copy. Okay? Yeah. Because when you do the transition, suddenly you need to spend use a lot of CPU time, this peak part, to do the data copy. Okay? Yeah. And how long? Yeah, so this peak. Yeah, so we imagine about 2 or 3 seconds. That's the peak time. Okay? 2 or 3 seconds. Yeah. All right. And we know our customers won't be happy waiting this kind of 2 or 3 seconds. Yeah. Every even 1 or 2 hours, then 2 or 3 seconds waiting. It's still very bad. Okay? All right. So now we want to, cut off this peak. Okay? We want to find a solution, still do the data copy, data transition, but without that kind of peak. Okay? Yeah. That means we spread the whole data copy work. Yeah, yeah, because when you do the data copy directly, you complete the data copy in a short period of time, right? Yeah, short period of time. Then the peak is very high, all right? How about we expand the data copy period, okay? Much wider, yeah, the data copy period. Then the time used, yeah, every time we do data copy, the time used, much shorter, right? Yeah, so much shorter, yeah. So we flat out the CPU consumption time, okay? Yeah, so we flat it out, yeah, like this, okay? All right, yeah, yeah. And technically, we can make it happen, in a relatively easy way. Yeah, we can make it happen, all right? Yeah. Here, the idea is pretty simple, all right? I just described the general idea. Yeah. So if you need to solve this problem in some real world situation, yeah, so you can think about this. Yeah. Remember the threshold, right? Yeah. So we need to set threshold. Let's say we set 90% of the capacity as the threshold. Capacity as the threshold. Okay? 90%. Yeah. We know the capacity, right, of an array. When you reach the 90% of the line, then you need to start to do preparation, transition of your data preparation. Okay? Yeah. As soon as you reach the 90% that capacity line, you need to create a new array. All right. The new array, how large is the size of the new array? Double the capacity of the old array. Yeah. So usually people do this one, double the capacity of the old array. Okay? Now, that's the most frequent way people use, yeah, to handle the size, yeah, array size. All right. All right. So then, after that, so you have a new array, okay? Yeah. All right. Then the next time, one new data item comes in, yeah, because after you reach the 90% line, now, every time when one new data item comes in, yeah, you need to copy 10 old data items from old array to new array. How about that? 1:10 ratio. Yeah, look at this 1:10 ratio. One new data item comes in, then you copy 10 old data items from old array to new array. So you only copy 10. Because when you copy 10 data items, it's very fast. Think about 2 or 3 milliseconds enough, right? 2 or 3 milliseconds enough. Then your customers won't feel the difference. The waiting time only 2 or 3 milliseconds. Then nobody can feel it. Okay? All right. Then 1:10 ratio. Yeah. Remember, when the remaining 10% comes in, you copy the 100%, right? Because 1:10 ratio. Yeah. The remaining 10%. Yeah. Yeah. But you copied it 10 times, right? Yeah. Yeah. When you accept the new 10%, yeah, but based on your copy ratio, you copy the 100%. Yeah, things like that. But nobody can notice the copy delay, right? Nobody can notice it. Yeah. Yeah. So using this kind of idea, so you can handle the huge data copy delay problem. Huge, 1 million, even 1 billion, you can handle it gracefully, right? Even, your array size as big as 1 billion data items. You use this graceful way, you can improve your customers' experience using your application. Yeah. All right? Yeah. So that's that. 8.3, heap property. Yeah. So I hope I complete the definition of parent-child relationship before the end of this class. Yeah, very simple definition. Yeah. All right. So heap property. Yeah. First, we need to, define a relationship among heap nodes. All right. Binary tree stored in an array. Yeah. All right. So then we need to work on each element in the array corresponds to one node in this binary tree. Okay. Yeah. In a binary tree. But it's an imaginary binary tree. Okay? Yeah. Yeah. Visually, we cannot see binary tree. All right? Yeah. So in our mind, we imagine a binary tree. Yeah. Corresponding the concrete storage locations in an array. Yeah. All right. Look. Yeah. But each node we use an array index to determine the location of that node. Array index. Okay. All right. Then, when we consider the relationship between two nodes, how do we describe relationship between two nodes? Yeah. So we use the relationship between two indices. Two indices. Yeah, we can control easily, right? Yeah. Control relationship between two indices of nodes. Yeah? So we find a simple way to, describe parent-child relationship. Yeah. So let me use a simple diagram to define this parent-child relationship. Yeah. Three nodes arranged in this local triangle. P represents P node, parent node. All right? Capital L represents left child node. Left child node. Capital R represents right child node. Their corresponding index. Parent node, suppose we use index I. Then, which element we want to choose as its left child? Double the index. Doubling the index of the parent node, 2i. Yeah. So the 2i node, we choose it as the left child node of the parent node with index I. Then, right child, 2i plus 1. The element with index 2i plus 1, so we choose that one, that element, as the right child node of the P node. Yeah. That's the, parent-child relationship we use in this heap data structure. Yeah. Yeah. So that's the rule. We follow this rule. Okay? Yeah. Yeah. All right. Yeah. Although here you can see there is no link, right? No concrete link. Yeah. So P and L relationship, there is no concrete link between them, but there is a soft link, right? I to I, this math relationship, we use a math relationship, double. Yeah. The number is double. Yeah. This math relationship as the soft link between P and L. Okay? Yeah. Similarly between P and R. Yeah. All right? In this way, we don't need to use linked list. Right? Yeah? Yeah. So we use, imaginary soft links. Yeah. All right. But for this kind of definition, we cannot use the index I equal to 0. No. So the 0 location cannot be used as a node in the heap data structure, because when you double the 0, you get 0, right? Yeah. So when we double the index number, we want to get a different location. Yeah. So only the first location cannot be used as a heap node. Yeah. That's okay. Yeah. Only one location we cannot use. Yeah. Yeah. So not too bad. Yeah. All right? Yeah. Yeah. So with this, now, after this definition of parent-child relationship, now we feel comfortable. So we can store a near complete binary tree in an array in the simple way. Okay? Yeah. Using soft links, a simple way. Yeah. Imaginary soft links. We can store an imaginary binary tree in an array. Yeah. All right. Yeah, that's simple. All right. Yeah. So relationship of one heap node. Yeah. Right. So here. All right. Yeah. So we reach the end. Yeah. All right. So let me see. Yeah. All right. So this kind of thing, heap types. Yeah. So let me leave next time. Yeah. Because we need to talk about the order information, order properties for the nodes in a heap. Yeah. So let me do it next time. Yeah. Yeah. All right. So now we finished the data structure description. Right? Yeah. Underlying data. The next time we need to work on this data structure. Okay? To complete the sorting. Yeah. All right. Heap sort. Satisfying those 3 business requirements. Yeah. All right.